Hey, welcome to Gold Scratch. So how do you tell if you got a forged crankshaft or not? You go like this. That's the sound of a forged crankshaft out of my customer's 409. And we got that and a whole bunch of other stuff to show you today. This is the second video on Brett's 409. The first one, we had the intake manifold off, the camshaft checked out. Now it's completely apart. And I've done all the dimensional checking. I'm going to share with you not only all the findings, but how I got them, how to use a dial bore gauge, how to read a micrometer, how to determine clearance in an engine using a dial bore gauge, and a bunch of other stuff. So if you're interested in that, hang with me to the end. I think you'll find it helpful. And before you do that, please like and subscribe, share. We need you guys to help us out to keep going, because right now I'm not building engines, I'm talking about it. So if you can help me out by doing all those things, it makes it worthwhile. Okay, so back to where we're at. I guess one of the first messages I have, and if you want to restore a car and you want the original engine, I've got customers who scatter the country trying to find all the right parts and drive there to get them. And this is a case. I don't know the exact history. I know Brett's had this engine for a long time. But in the first video, I already shared some things that were wrong with it because we had an option of actually starting it up, which would have been a disaster if I had done that. And as we delved into it, you sort of peel back the onion, you find out more and more things wrong. It motivated me to take it right apart, and a good thing I did, because I found lots of stuff that's not very good. So it looked great on the outside, and obviously someone made the comment on the previous video, it looks like a guy had a bunch of parts and he put them together to make an engine. And that's kind of what looks like it's happened. So the other thing is, this engine is either going to be fixed right or it's not going to be fixed at all. So I'm going to go through the whole process for you. And the first step we're going to do, if we go forward, and I need my customer to be agreeing to that, is to get this block to the machine shop, get it fully checked out, and make sure that it's a usable block, and everything else we can get. So one of the other things, Alec and I often talk, and I'll mention something and Alec will say, does everybody know that? And maybe not, probably not. Let's show them. So that's kind of what we're going to try and do today. People watch videos for really a couple of reasons. One is to be amused or entertained, and the other one is to learn something. And I'll never make it as an entertainer, so I'm going to try and, if you're interested, teach you some of the things, share some of the things that I know how to do. Lots of guys know that and a lot more, but for those that don't, hang with me and I'll try to make it interesting. I'm going to show you how to use a dial bore gauge, how to use a micrometer, how to check out. We'll have a screenshot up of all the dimensions I've done, checked out the clearance on every bearing, crankshaft rods and mains, and the pistons, cylinder wall clearance on this engine, and the results are not very good. So we're going to go through that with you today. So one of the things is to check out the parts, and I started by doing this. So if Alec comes in here, one of the things you want to know is, do you have a forged crankshaft or do you have a cast crankshaft? So if you want to come in a little closer, I like to look, and I can show you how you can tell the difference. If you look at the parting line, a forged crankshaft, when it's hot forged, it starts with a solid piece of steel. There's two knives come down and they shear at the parting line. So you have this shear mark at the parting line of the cylinders, of the crankshaft from the top and bottom. If this was a cast crankshaft, as opposed to being a forged crankshaft, you see a very, very sharp, small line there instead. And that's because it would have been cast, so it had a mold, and the two halves of the mold come together, and where the two halves of the mold come together, it makes a little parting line. So at least we know Brett's got a forged crankshaft, and that's good. And actually, I've checked all the dimensions on the crankshaft. It's been turned 10 thou. Probably going to turn it more, because they're not, actually the crankshaft is big, and so in other words, the dimensions are a little bit oversized, and that when I did all the dimension checks, I'm going to show you the bore, but then the same process, some of the bearing clearances are only a little over 1/1000th of an inch, which is not enough for a high performance engine. So we're probably going to regrind this crankshaft. One of the big issues with 409s is getting parts, and getting parts is, when you're doing restoring old engines, always very time consuming, big problem. And sometimes we get parts from all kinds of different places. But if you got a 409, these are probably one of the best suppliers. They're in Minnesota, Show Cars. They specialize in 58 Chevs, 59 to 64 Chevs. So the engines that use 348s and 409s. And this is an old catalog. I bought this catalog when I did my first 409, but they're online. I checked the part numbers and stuff. It looks like they're all still available. And we will probably be going to these guys for parts if we go forward with this engine. So one of the things that we had to do was I checked out the crankshaft, and once again, it's not bad, and we'll have to get it, take it to the machine shop. I'll be using Atchison's. It'll be washed, magnetic particle inspected, which is a way to determine if there's any cracks in it, and probably turned and ground, reground and polished to an undersize. And according to Show Cars, you can get bearings, I think, right down to 40,000ths undersize. I think in the mains even down to 60,000ths. We don't need that. 20,000ths will do the job here. So, and back to the block. This block's already bored 60,000ths, but based on the homework that I've done, you can actually bore 409 up to 125,000ths. And Show Cars has pistons for it up to 125,000ths oversized. Now, it's already bored 60. What we would do is to determine if we're going to use this. The first thing is it'll be sonic tested, it'll be pressure tested, and magnetic particle inspected as well, and determine what's the minimum size that we can get to clean up the bores, and that'll be the size we use. So if it's 60 now, hopefully at 80,000ths, we can go to 80,000ths. We can buy pistons that are 80,000ths according to Show Cars. So that's a problem that can be solved, and we can go ahead and do that. And that'll be one of the determinations: is get the block there first, make sure it's good. It doesn't have cracks or anything. It can be pressure tested, magnetic particle inspected, and then what bore it needs to be to clean up. And we start buying parts based on that. Probably turn the crank another 10,000ths of an inch, and we got ourselves a good usable forged crank, and we'll check it out as well. So I'm going to show you how we check clearances, and I'm going to use one piston for an example. Maybe I'll show you before I do that what really brought us to the point of when I did the leak down test in the first video. I said the leak down varied from 25 to 60%, and I showed a spreadsheet on that video, and the worst cylinder was number 8 cylinder at 60%, and here is why. So someone has, this is called knurling, and there is actually a legitimate process to do that, but I think in this case it's been abused. By rolling a knurl over the piston, what it does, it extrudes a little bit of metal and makes it a little fatter, I guess, a little bigger in diameter. And that's kind of a terrible way to fix a high-performance engine. Back in the day, knurling was fairly common, and nowadays I don't think I haven't seen a piston knurl for a long, long time. Anyway, and this piston went in number 8 cylinder. It had 60% leak down. This cylinder is, the rest of them are 60,000 oversized. This one's 75,000 oversized. I don't know how it got there, what the story is or whatever, but it's excessive. This piston would have been rocking all over the place if I ever started up this engine. So buyer beware. And when you buy something like this that's complete, how do you know that? You don't know unless you take it apart. So that's the problem, and that's where we're at now. However, everything that we are talking about can be fixed. And if we overbore it, we'll obviously buy new pistons anyways. And the next thing is the rods. By the time we spend money pressing the pistons off, have the rods reconditioned, change the rod bolts, we'll probably buy new rods as well. So new rods, new pistons. This crankshaft hopefully stays. So I'm going to show you, first of all, how we determine piston clearance. So just back to we use the same process using a dial bore gauge and micrometers. And for crankshaft clearances, you can use a thing called plastic gauge. It's just a little piece of plastic basically that goes in, you bolt it down and measure the thickness. And back in the day, that's what I used, but there's a better way to do that now, and that's a dial bore gauge. One of the problems with plastic gauge, you got to put everything together, take it back apart again. So it's a lot more time consuming, a lot more work than this, and this is a lot more accurate as well. So for an example, if I get Elliot to come in here, well, we come in, let's digress for a second. I talked about the cylinder heads because we've got the camera close to us. How unique the cylinder is. That's a 409 cylinder head. As you can see, there is no combustion chamber. I think there's about 15 thousandths of volume in this part of the cylinder head, but basically no combustion chamber. And as I showed in the previous video, combustion chamber is in the cylinder, not in the head. As compared to that's a typical small block head that I happen to have. There's the combustion chamber. It's the opening in the head, and then the piston. Typically, you use a flat top piston, and all the combustion chamber volume, usually around 64 cubic centimeters (cc's), is in the cylinder head. So, just to show that. So, one of the things before we do the dimensional check, let's look and see what we're looking for. So, if you go to a 409, the standard bore is 4.312. And so this is bored 60 thou over. So if you add 60 thou, if I measure the bore, it should be 4.372. So if you're going to do something like this, customer recently sent me an email saying, you know, what tools do you need to build an engine? And I send them a pretty good list, I think, anyways. And someday we'll make a video, we'll lay out all the tools that you do need to do an engine properly and show you that. But one of the things you need is a set of micrometers. Now, this is a complete set, but which ones do you use? Typically, the 2 to 3, which is on my micrometer stand right now. Micrometer, and because almost all crankshaft journals are between 2 and 3,000. So that's the one that's most commonly used. And then the other one is for measuring pistons, 4 to 5, because most pistons are somewhere between 4 and 5 inches. And you might use 3 to 4 sometimes. If you did a 307 or 283 or something, they're less than 4 inches. But almost all bores, you know, in recent engines anyway, are at least 4 inches. So the 4 to 5 might get used. And this one's never been out of the bag. Maybe someday I'll do a big diesel or something. But other than that, it probably won't get a lot of use. So the next is the dial bore gauge. So it's actually pretty simple. And if you buy a dial bore gauge, it has all these different sizes of extensions that you can put. So right now I've just got this one on. So that's how simple it is. You just have to pick the one that gives you the right amount of measurement. So that came out of there, and it's kind of a trial and error unless you remember which one you used. And because they're hard to handle, I use these little tweezers because if it's not exactly on, you can adjust it by using these little guys. Okay, if I can get a hold of one for you. So there you go. So that goes in behind here to give you the exact sort of range of motion that you need. So how does it work? So there's a little plunger at the bottom. So I might as well turn this over and push on the plunger from here. And as you rotate it in the bore, it moves your dial, and that's how you determine it. So what's the benefit of a dial bore gauge? One of the other ways we used to do it is you you'd measure the bore and you'd measure the piston and you subtract one from the other. Now you got, you're checking to 4-dimensional points, adding and subtracting, and measuring to 4-dimensional points, and adding, subtracting, trying to get an answer. A lot easier to make a mistake. When you use a dial bore gauge, you measure the piston. I'm going to show you how we do that. Then you transfer that measurement to the dial bore gauge, and you take the dial bore gauge and put it in the cylinder. So instead of measuring the 4 percentage points, dimensional points, you're measuring one. It's either 1 thou or 2 thou or 1.5 thou or whatever it is. It's much easier and it eliminates a lot of opportunity for error. So the first thing we have to do is take the micrometer and measure the bore, measure the piston. And the other thing that's important to know, we measure the piston, we transfer that measurement to the dial bore gauge, check the cylinder, determine the clearance. It doesn't really matter what the piston is. It doesn't even matter what the bore is. It only matters what the difference is. So, although we do record all that anyways, but once again, the only thing that's important is what the actual dimension is. So we stick to typically the widest part of the piston. Now, sometimes that's right opposite the pin or a little lower than the pin. So we slide that through. I've already got it kind of pretty close there. Just enough that you're not distorting your gauge or anything. And I've got it locked. I've already done that. So how do you determine how much that is? So Elliott's going to come in here and we're going to read off what the piston was. So it's a 4 to 5 micrometer, 4-inch to 5-inch micrometer. So we know we're starting at 4 inches. Okay, minimum's 4 inches. So each of those increments is 100 thousandths, the big increments, 1, 2, 3. So we know it's 4.3 something. And then each of the little lines is 25 thou. So if we add here 4.3, and then we've got 2 little lines, so that gives me the 050. And then in addition to the 050, there's 20, so it's not quite 20, so it's 19. So it's 019. And then how do you get the tenths of a thou? You go over here and you find out whatever line lines up from this side of the micrometer to this side. Okay, so I'm saying the 3 lines up pretty good. So that's 3/10 of a thou. So this piston is 4.3693. You just add up all the numbers. And that's how you get your measurement on a micrometer. Now, lots of guys watching this know this better than I do, but there's people watching that have never seen it. So I'm going to try and show you, and hopefully that's going to be helpful. So the next thing I do, once again, even though I record all that, it doesn't really matter what it is. What matters is what's the difference between the size of the piston and the size of the bore. So this is the little tricky part. It takes a little bit of feel to do it. And I should have my micrometer base bolted down to the bench, but I don't. So if you look at the gauge, Alex, so I rotate it so I basically get 0 clearance on the gauge. So I think I'm a little bit up. It's pretty darn close there, eh? Close enough for demonstration purposes. Take the same gauge. Now that's 0. So if I go into number 6 cylinder, because that's number 6 piston, and rotate it through, and if I'm measuring it near the top, I got about 5 thousandths. So there's the 0. If there was no clearance, it would come back to 0. So I got about 5 thousandths. Now here's the other thing to show you. If I go down to the bottom of the cylinder, I only got about 3 thousandths. That tells me there's about 2 thousandths of an inch taper in the cylinder. Okay? There's only about 3 thousandths at the bottom where there's no wear. And at the top where there's wear, there's 5 thousandths. So the cylinder's got a couple thousandths of an inch taper. And when I did the dimensional checks, we'll show that on the spreadsheet. I took 2 measurements. I took one at the top and one at the bottom, so we can do that. Here's the other thing. I showed you number 8 piston. Okay, so let's go back to here, Alec. And so let's 0 the gauge in number 6 cylinder for now. Pretty close. And put it in number 8. About 16 thousandths. It should come back to 0. So 5, 10, 15, 16, or 17 thousandths. So somehow this hole got, instead of 60 thou over bore, 75 thou over bore. And I don't even know how you explain that, but it has to be fixed, obviously. So we're going to have to be boring this engine at least another 20 thousandths. Hope you found that helpful if you've never done that before. Now, this tool is only about $100 and probably maybe even less. I don't know. Had this for a long time. Probably made in China. Who cares? A thousandth of an inch in China is the same as a thousandth of an inch here, so it doesn't really matter. It measures accurately. It gives you good results, and the variation. This thing goes everywhere from 2 inches right up to probably 6 or 7 inches bore, something like that. Definitely everything that I need to ever do, and a reliable tool, and the order of magnitude of error is much less using a dial bore gauge. So if you're going to do more than one engine, probably worth investing in doing that. So what have we covered? Where we're at? Here's another thing, the interesting thing. We talked about the cylinder when we had the last video. The cylinder heads were still on. So you can see that the bore of the deck of the block, I think it's 72 or 74 degrees, instead of being perpendicular to the cylinder bore. So that makes the cylinders, top of the cylinders aren't a circle. They're an oval. And what that also did for them at the time was allowed more room for the valves, because one of the problems when you keep using bigger valves in a small bore cylinder, the valves are going to start hitting the block, so you can't have that. So that actually allowed the exhaust valve at the bottom to have a little more room, and they squeeze that around. So, when you think about, what we're doing with engines now, and the guys that designed stuff like this in 1956 or something like that, we're just tinkering compared to the guys that designed this and decide the mold for it and the pattern for it and all that kind of stuff. Pretty smart guys. But the 409, that's also the problem with the 409. It just never breathed as well as the 396 or 427 that followed behind it. And it wasn't great for real high RPM. You can buy all kind of elaborate parts for it and go there, but you're probably never going to find the performance you'd get in a big block 427 or something like that. That's also the limitation of it. And so that's why it got replaced, but it's the value is not in its horsepower potential as much as it's iconic. And if you got a 58 to 64 Chev and you want to restore it correct, that's your only choice. So I hope you found that helpful and interesting. Where do we go from here? I've sent my customer a list of a report on Word, all the details that I'm sharing with you now. And I've sent him a spreadsheet, which we'll put up with all the dimensional checks that I've taken. And I sent him an estimate for what it's going to cost to fix this. And it's up to him to decide what we want to do next. Step one, get this block to Atchison's, make sure we've got a good block and how much we need to bore it. And we'll go check the crankshaft, make sure the crankshaft's not cracked, and go from there. If we do that, everything else we can buy, all the other parts we can buy. Hope you found that interesting. If you did, if you haven't subscribed by now, it's not too late. You can always do it now, right? So if you enjoyed this video, if you found it helpful, please like and subscribe. Thank you for watching Gold Scratch.